Hi, so this lesson is on the alternating series, including the alternating series remainder. It's lesson 9.5. Okay, so lesson overview. I'll show you how to use the alternating series test to determine whether an infinite series converges or diverges, how to classify a convergent alternating series as absolutely or conditionally convergent, and how to use the alternating series remainder to approximate the sum of an alternating series. Okay, so to get started, here's my explanation of the alternating series test. So, in this case, a sub n is the non-alternating part of my series. So, a sub n is greater than 0. So, the alternating series, the sum from 1 to infinity of -1 to the n times a sub n, and the sum from 1 to infinity of -1 to the n plus 1 times a sub n. Those are just like two different forms of alternating series. One is positive on negative numbers. One is negative on even numbers, and one is negative on odd numbers. So those two types of series converge if the following two conditions are met. So first of all, the limit as n approaches infinity of the non-alternating part of the series must be 0, and the non-alternating part of the series must be non-increasing for all n. So a sub n plus 1 has to be less than or equal to a sub n for all n, which can be proved by either finding out a sub n plus 1 and a sub n, or by doing the derivative test to show decreasing. Okay. If the limit of the non-alternating part of a series, a sub n, is 0, and the non-alternating part of a series is non-increasing for all values of n, then the alternating series converges. However, this does not mean that the infinite series containing just the non-alternating part of a series, which is represented by a sub n, would converge on its own. So, note that this test only confirms that the alternating series converges conditionally. So, what I'm saying is that just because the alternating series test works and you determine that the alternating series converges does not mean that the non-alternating part of a series, a sub n, will converge on its own. Alright, now here's my explanation for classifying a convergent alternating series as absolutely or conditionally convergent. So, in this case, a sub n is the whole alternating series. It's the whole entire function, including the -1 to the n or to the n plus 1. So, the sum of a sub n is absolutely convergent if the sum of the non-alternating part converges. So, the absolute value of a sub n, meaning it's always positive, it's no longer alternating. But the sum of a sub n is conditionally convergent if the sum of a sub n converges, but the sum of the absolute value of a sub n diverges. So, an alternating series is conditionally convergent if the alternating series converges, but the non-alternating part of that series does not converge. So, when the non-alternating form of an infinite series does converge, then the alternating form of that same series converges absolutely. However, when the alternating series test shows that the alternating series does converge, but the non-alternating form of that infinite series does not converge on its own, then the alternating series converges conditionally. Note that you should not test for conditional or absolute convergence until you have shown that the alternating series test works and the alternating series does converge. Alright, here is my explanation for approximating the sum of an alternating series using the alternating series remainder. So, in the white box you can see the equation, but I'll simplify that for you. So, if a convergent alternating series satisfies the condition a sub n plus 1 is less than or equal to a sub n, meaning that a sub n is always non-increasing, then the absolute value of the remainder, which is represented by r sub n, involved in approximating a sum, which is represented by s sub n. So s sub n is an approximation. Then the error in that is less than or equal to the first neglected term. So the absolute value of s minus s sub n is the error, and that is equal to the absolute value of the remainder, which is less than or equal to the first neglected term. So, if the sum of an alternating series is approximated by adding up the first n terms, then the error in that summation approximation is less than or equal to a sub n plus 1. Note that the sum of an alternating series can only be approximated if the alternating series has confirmed that the series converges, either conditionally or absolutely. So this won't work if the alternating series does not converge. If it diverges, then you can't approximate the sum. Alright, here is example number 1. Determine whether the alternating series is convergent or divergent. If it's convergent, classify it as either conditionally or absolutely convergent. So we're given the alternating series, the sum from 1 to infinity of negative 1 to the n over the square root of n. And then those 4 terms show you the first 4 terms. So I started by letting a sub n equal 1 over rad n, which is the non-alternating part of the series. So, step 1. You do the alternating series test by showing that the limit as n approaches infinity of a sub n equals 0, because the limit as n approaches infinity of 1 over rad n is 0. And the a sub n is non-increasing for all n because 1 over radical n plus 1 is less than 1 over radical n. So therefore the alternating series test works and the alternating series converges. We are unsure of whether it converges conditionally or absolutely. That is what we determine in step 2. So step 2. We have to show that the so the non-alternating form of this infinite series is a p-series, where p equals 1/2. So by the p-series test, we can conclude that it diverges because p is not greater than 1. So we all know that a sub n equals 1 over rad n, which is equal to 1 over n to the 1/2. And therefore we know that p equals 1/2, and by a p-series test, it will fail the conversion. It will not converge because p is less than 1. Therefore, this alternating series is conditionally convergent because the alternating series converges, but the non-alternating series diverges. Okay, here is example number 2. So we are going to approximate the sum of this alternating series using its first 6 terms. And the series is the sum from 1 to infinity of negative 1 to the n plus 1 times 1 over n factorial. For n factorial. Okay, and then I gave you the first 6 terms. Alright, so step 1. We use the alternating series test to show that the alternating series converges. So I showed you that the limit as n approaches infinity of the non-alternating form, so the limit as n approaches infinity of 1 over n factorial is 0, and a sub n, which is 1 over n factorial, is always non-increasing, since 1 over n plus 1 factorial is always less than 1 over n. So therefore the alternating series converges. Step 2. We found the sum of the first 6 terms. So at the top I gave you the first 6 terms, but you just have to FOIL that out yourself. So the sum s sub 6 is the sum of the first 6 terms, and that is approximately 0.63194. That's just from using your calculator to add those all together. Step 3, we find the alternating series remainder. Since we did the first 6 terms, the alternating series remainder will always be less than or equal to a sub 7, since 7th is the first neglected term. So a sub 7 is 1 over 5,040, which is approximately 0.0002. Therefore, the most the error could possibly be is 0.0002. So, the sum of the alternating series must lie between 0.63194 minus 0.0002 and 0.63194 plus 0.0002, meaning that the sum is between 0.63174 and 0.63214. Alright, I hope that made sense. And here is your homework problem number 1. Determine whether the alternating series is convergent or divergent. If it's convergent, classify it as either conditionally or absolutely convergent. That was the first example we did. And there in your white box is your alternating series.